This is the fifth video in my series of videos on Edmund Landau's Foundations of Analysis. In this video I'm going to be continuing with what I started in the last video on cuts, but here I'm going to be focusing on rational cuts and integral cuts. So I'm going to get straight into things here. So definition 39 says that a cut of the form capital X star is called a rational cut. So if you remember the notation that was introduced in the last video, the cut X star is the cut, the set of rational numbers which contains all rational numbers less than X, which we showed in the last video is actually a cut. And definition 40, a cut of the form lowercase x star is called an integral cut. So lowercase x's, lowercase letters are typically used at this stage for to indicate, to represent integers. So x star is going to be called an integral cut. Theorem 154 shows that if x is greater than y, then the cut x star is greater than the cut y star. Similarly for x equals y, x star is equal to y star. So here we've got rational numbers and here we've got cuts. So Theorem 154 shows that there's a very clear relationship between the ordering of rational numbers and the ordering of rational cuts. And this is going to be quite significant before the end of this video. This is going to be quite a significant bit of information really regarding the relationship between rational numbers and rational cuts. So I'm not going to prove that. I've got a couple of theorems that I'm wanting to go through in some depth in this video, but this is not one of them. Theorem 155 again just gives some relationships between rational numbers and cuts. So if I take the sum of the rational numbers x and y and I form the cut relating to that rational number x plus y, then this is the same as if I'd found the cut corresponding to x and the cut corresponding to y and found the sum of the two cuts x star and y star. And similarly for x minus y, x times y, and x divided by y. So I'm going to prove the first one here and I'm not going to bother proving the other ones. I'll prove the first one just to give a bit of an idea about how this goes. So typically if you want to show that two cuts are equal, thinking back to the definition of equality of cuts, what that means is that every lower number of this must be a lower number of this, and every lower number of this must be a lower number of this. It doesn't suffice just to show in one direction. For example, every lower number of this is a lower number of this. That wouldn't suffice. You need to show in both directions. So that's what we're going to have to do here. So let x1 be a lower number for x star, for instance, and also y1 a lower number for y star. Then by definition the cut x star plus y star is the set of rational numbers of the form x1 plus y1, where x1 is a lower number for x star and y1 is a lower number for y star. So certainly x1 plus y1 is a lower number for x star plus y star, and that's just by definition really. But since x1 is a lower number for x star, and x star is the set of rational numbers less than x, then that means that naturally x1 has to be less than x, and also y1 has to be less than y for the same reason. And from this we can conclude that x1 plus y1 is less than x plus y. So this is a theorem that's proved in the section on rational numbers. It's one of the ones that I missed out. It's a fairly trivial theorem, but as I've said before, even though they're trivial, the theorems, it doesn't mean that they're useless. They're actually often quite useful, albeit trivial. So if x1 plus y1 is less than x plus y, remember that x plus y star is the set of all rational numbers less than x plus y. So therefore x1 plus y1 must be in the set x plus y star, which is a cut. So therefore x1 plus y1 is a lower number for x plus y star. So what we've shown here is that any lower number for x star plus y star must also be a lower number for x plus y star. Now we need to go in the other direction. So let u be a lower number for x plus y star, then naturally u has to be less than x plus y. Again, just to reiterate, x plus y star is the set of all rational numbers less than x plus y. And then using a similar kind of argument to Theorem 129, which I proved in the last video, we can show that u over x plus y is less than 1. And that leads us to the two situations, x times u over x plus y is less than x times 1, which equals x, and y times u over x plus y is less than y times 1, which equals y. So how these are coming about might be worth looking back. If you need a reminder, look back in the last video, Theorem 129, and it's a very similar kind of argument. And from this point forward, it's almost identical actually to what happened in there to a certain extent in Theorem 129. So that means that this x times u over x plus y is a lower number for x, and y times u over x plus y is a lower number for is a lower number for x star, and this is a lower number for y star. So therefore x times u over x plus y y times u over x plus y, this must be a lower number for x star plus y star, because it's a sum of a lower number for x star and a lower number for y star. So this is equal to, you kind of factorize this, you get x plus y times u over x plus y, which is equal to u. So what we've shown here then is that our arbitrarily chosen u, which was a lower number for x plus y star, is also, by what we see here, is also a lower number for x star plus y star. So we've shown this now in both directions. Every lower number for x star plus y star is a lower number for x plus y star, and every lower number for x plus y star is also a lower number for x star plus y star. So u is a lower number for x star plus y star, which is exactly what we needed to show. And the other propositions, they're not identical obviously to this, but they run along similar lines. You need to show in both directions that a lower number for this is also a lower number for this, and vice versa. So that finishes up with this theorem. The next theorem that I'm going to move on to is a really important theorem in the development. Let's have a look now at Theorem 156, which what we want to show here is that the integral cuts that I've just defined previously satisfy the 5 axioms of the natural numbers. If the role of 1 is assigned to 1 star, and if we set x star primed equal to x primed star. So this is a fairly straightforward routine thing to do. So we just need to go through the individual axioms one by one and show that they're all satisfied. So actually I don't need that right now. So I want let, and we're back to this funny symbol that I've used it in a previous video. I've still no idea what it means. So B star maybe. B star be the set of all integral cuts. Okay, so then 1 star belongs to B star. 2, so the second axiom was that every number has a successor. So let's say we've got x star belongs, so if x star belongs to our funny symbol set, then we know that from this definition up here that x star primed is equal to x primed star. So because x primed, if x is an integer, then x primed is also an integer, then x primed star is going to be an integral cut. So x star primed is an integral cut, and therefore the successor of x star is also in our set. So x star primed belongs to funny symbol set. 3, we need to show that 1 star is never going to be a successor of any number. So we know that because the integers satisfy the 5 Peano axioms, then we know that x primed is not equal to is not equal to 1. But these are rational numbers. Now think back to what I showed at the start of this video, Theorem 154. If rational number x equals rational number y, then x star is equal to y star. X is greater than y, rational number x is greater than rational number y, then x star is greater than y star, etc. So that means that determines that tells us, should I say, that x primed star is not equal to 1 star. So remember, integers are themselves rational numbers, but x primed star is equal to x star primed. So x star primed is not equal to 1 star. So therefore, the successor of x star is never equal to 1 star. So 1 star is never a successor. Part 4. So we need to show that if two successors are equal to one another, then they must have come from equal numbers, or equal cuts in this case. So if we've got that x star primed is equal to y star primed, then we can use this definition here to say that x primed star must be equal to y primed star. But again, theorem 154 tells us that using the converse direction, we'd get that x primed is equal to y primed, but integers satisfy the 5 Peano axioms, so x primed equals y primed means that x must be equal to y. So finally we can say that x star must be equal to y star. So if two successors are equal, they must have come from the same number, or in this case the same cut. And then for part 5, okay, so let m star be a set of integers, of integral cuts, sorry, such that one star belongs to m star, and 2 if x star belongs to m star, then so does x star primed. So in other words, if for any cut that is in our set m star, then the successor is also. So now so this is quite similar to what we did for the case for rational numbers, or for integers should I say. It's just the notation slightly different, that's all. So now let m be the set of integers such that x belongs to m if x star belongs to m star. So therefore 1 is in m, because 1 star by definition belongs to m star, and if x is in m, well, x is in m only if x star is in m star, which we know that x star belongs to m star, but if x star belongs to m star, then x star primed belongs to m star. So if x is in m, then x star, x primed belongs to m. So here we're kind of using the fact that, so I'll just put it over here, this is equal to x primed star, which is allowing us to make this conclusion that x primed is going to belong to m. So therefore m is the set of all integers, so m is the set of all integers so therefore m star must be the set of all integral cuts. So m star is set of all integral cuts. So just squeeze that in there. So that shows that the integral cuts satisfy the 5 Peano axioms, the 5 axioms for the natural numbers. So what happens now is similar to what's happened previously with the integers. When we showed that the integers satisfy the Peano axioms, the natural numbers got thrown out and in came the integers, but along with the integers came the rational numbers. So we were throwing out this old number system from the natural numbers, bringing in this enlarged number system, the rational numbers, which had a subset, the integers, that behaved in exactly the same way as the natural numbers. So there was a clear advantage to doing that, because we replaced an old system with a new enlarged system. Well, a similar thing's going to happen here. We're going to throw out the integers and the rational numbers, and we're going to bring in integral cuts and rational cuts to replace them. In fact, cuts in general. So, but there's a bit of a catch here, because previously, when we replaced naturals with integers and rationals, we clearly had something new. We had the integers, but we also had the rational numbers that were not integers. So we had extra numbers, which we didn't have before, which was a clear benefit to us. But in this case, we replaced the integers and rational numbers with integral cuts and rational cuts, but we don't actually know if there's anything extra that's been brought along. So that's what we're going to be showing in the rest of this video, that actually once we've replaced the integers and rationals with integral cuts and rational cuts, there is actually something else that's come along with these cuts that are neither integral cuts nor rational cuts. So there again is a very clear benefit to doing this. It's just we don't know about it just yet. So that's what we're going to look at in the rest of this video. Okay, so I didn't have space on the board before for this, but this is definition 41, and this brings in a new meaning for our notation. So just like with when we brought in the integers and we got rid of the natural numbers, we changed the meanings, or the meaning of the symbol, for example x, from a natural number to an integer. Well, now the symbol that we used to use for rational number x is now going to replace this notation, this x star. So x star is what we've called the rational cut, determined by the rational number x. But now we're going to get rid of this, because we don't really need rational numbers anymore, because we've thrown all of those out and we've brought in this new number system, these cuts. So it'll just make our life easier, really. So we will still refer to rational numbers. We won't refer to them as rational cuts. We'll just call them rational numbers, because I guess in a certain sense, to look at these two number systems, rational numbers and cuts, just looking at the rational cuts, they're identical in many ways. And I said earlier regarding Theorem 154 that this was quite a significant theorem, because it shows that if x is less than y, the rational number x is less than rational number y, x star is less than y star. X equals y, then x star is equal to y star. So the rational numbers and the corresponding rational cuts have all the same relationships to one another. So in a certain sense, visually, these two sets of numbers are kind of identical. It's just that with these cuts, as we'll see, there is a bit more there. Just like when we brought the rational numbers in, throughout the natural numbers brought integers and rational numbers in, we had more to work with. When we bring in these cuts, it turns out there is more there for us to work with. Similarly, the notation lowercase x, which has meant an integer to this point, will now be used instead of the notation x star. So we're going to get rid of that. We will still refer to this as an integer, so we won't call it an integral cut, we'll just call it an integer. Very occasionally we will need to still use the symbol x in the old sense. So if we call x a rational number, we could possibly mean it in two different senses. In the sense of definition 41, which is the most usual meaning that's going to be applied to this from this point forward, very occasionally we will need to interpret x as a rational number in the old sense. But this is usually, it's quite easy to spot. Either it's, particularly in Landau's book, he actually says that it's being interpreted in this sense or that sense, but there's only a couple of occurrences of it, and it's fairly easy to spot. But typically if x is being referred to as a lower number, then probably that means that x is being thought of as a rational number in the old sense. And if x is being, let's say we've got x is less than psi, then this usually means that x is being used as meaning a rational number in the sense of definition 41. Although there will be a theorem that I'll be going through in a second that kind of does away with the need to flip between the two meanings, and really does away with the need almost altogether of referring to rational numbers in the old sense. Okay, just a few theorems here that I want to state. I'm not going to prove any of these theorems because I've got the next theorem that I want to prove, which is quite a lengthy one. Theorem 157, the rational numbers are those cuts for which there exists the least upper number x. Then x is, this x is then the cut. I'm going to say a bit more about this probably towards the end of this video. This is, at this stage, this seems quite an unusual theorem, kind of insignificant, but this is actually a very significant theorem in my opinion, which I'm going to come back to in a few minutes. Theorem 158, let psi be a cut, x is a lower number. So here, this is where we've still got the little bit of ambiguity between the interpretations, maybe the meanings of this x. Well, x here is being referred to as a lower number, so this is this symbol x means a rational number in the old sense of rational number, if and only if psi is less, so x is less than psi. So here, because we're comparing x with a cut, psi, then x must itself be a cut. I can't compare a rational number with a cut. So here we're talking about a rational number in the sense of a rational cut, in the sense of definition 41. Hence, x is an upper number if and only if x is greater than or equal to psi. Again, x being referred to here as an upper number, that's rational number in the old sense. X greater than or equal to psi. Here we're referring to x as a rational number in the sense of definition 41 in the new sense. So this can save you a bit of hassle having to flip backwards and forwards between the two interpretations. There still might be occasions where you need to refer to rational numbers in the old sense, but through this it becomes less of a necessity for you to do that. You are a bit more freed up and able to interpret things more in the new sense of rational number and integer as well. Theorem 159, if psi is less than eta, then there exists z with psi less than z less than eta. So between any two cuts, there is always a rational cut. So at this stage, we're still in a bit of limbo, really, because we've not proved that every cut is a rational cut, nor have we shown that there is a cut that is not a rational cut. So we've got to leave it open at this stage, really. These might be rational cuts, they might be a cut of a different kind. We don't really know at this stage. We've just got to leave it a little bit open-ended. That question, that issue will be addressed very shortly. But what this is showing is that even if these cuts do happen to be something other than rational cuts, a different type of cut. We're not able to bring these kind of arbitrarily close together so that they're still different, but that there's no trace of the old number system, these rational numbers. These rational numbers are basically everywhere between any two non-equal cuts. You're always going to have one, in fact you'll have an infinite number of rational numbers. So they're really quite thoroughly spread throughout this set of cuts. There's not really any way to escape them, in a sense. And theorem 160, every z greater than psi eta may be brought into the form z equals xy with x greater than or equal to psi and y greater than or equal to eta. Quite an obscure little theorem. This is something that is used. So in and of itself, it's not very interesting. Limited interest at best, but it is something that is used in the theorems that are to follow. So there is a purpose for it there, and that's why I've included it here. So now we move on to theorem 161. So this is theorem 161, and it simply states that for each zeta, the equation psi times psi equals zeta has exactly one solution. So you could almost imagine this as kind of comparable to maybe a pure quadratic equation, but obviously here it's relating to cuts. It's not relating to real numbers or anything like that at this stage. I'm not too bothered about the uniqueness aspect of this. It's really the existence of the solution that I'm wanting to prove. So the way that we do this is we consider the set of rationals x with x times x less than zeta. Okay, so here the x's we are considering as cuts, rational cuts, but we'll call them rational numbers in line with definition 41. We need to show that this set of rationals that we're talking about here is itself a cut. So we've got to go through those criteria, 1, 2 and 3 in turn. So let's start with 1. We choose x to be such that x is less than 1 and x is less than zeta, which we can do because there's no smallest rational, so we can always do that. Well, in that case we get that x times x is less than x times 1. X times 1 is of course equal to x, and x is less than zeta. So therefore the x that we chose must be in our set because it satisfies the right conditions. So we've definitely got a non-empty set, which is good. And now choose x to be such that x is greater than or equal to 1 and x is greater than or equal to zeta. So in this case, again, such an x can be chosen because there's no greatest rational. So however large zeta is, if it's greater than 1, then we can just choose an x greater than zeta or greater than or equal to zeta. If zeta is less than 1, then we just choose an x that's greater than or equal to 1, and we can do this. So we get x times x is greater than or equal to x times 1, which of course is equal to x, which is greater than or equal to zeta. So x times x is greater than or equal to zeta. That doesn't satisfy this criteria here, therefore this x is not going to be in our set. So the first line here shows that this x, so chosen, is in our set. This shows that the x chosen in the second case is not going to be in the set. So we've got the first part done. 2, we need to show that for every number that is in the set, every number that is less than that chosen number is also in the set. So let's x be in the set and y less than x. Well, in this case we get that y times y is less than x times x, but if x is in the set, then x times x must be less than zeta, and therefore y times y is less than zeta as well, in which case y, this y which was arbitrarily chosen, must also be in our set. And finally we need to show that for every number in the set there is a number greater than that given number, that chosen number, that is also in the set. So there's no greatest number in our set. So let x be in the set so obviously that means that x times x is less than zeta, and now choose z so that z is less than 1 and z is less than zeta minus x times x divided by x plus 1. Okay, again, such a z can be chosen because there's no least rational. This makes sense because zeta, x times x is less than zeta, so zeta minus x times x exists. So this expression here makes sense. Okay, so let's have a look at x plus z. So x plus z times x plus z is equal to x plus z times x plus x plus z times z. So that's just using the distributivity, which is equal to, less than x times x plus, strictly speaking it will be zx, but I'm going to write it as xz plus x plus 1 times z, since z is less than 1, so that's where this inequality comes in. I've just changed the z to a 1, and that is equal to x times x plus, using associativity, xz plus x plus 1 z. Taking the z out using distributivity, x times x plus x plus 1 z. So this x plus 1 times z, if you think about it from this here, we can say that z, or x plus 1 times z is going to be less than zeta minus x times x. So, okay, that means that this is going to be less than xx plus zeta minus x times x, which is equal to zeta. So therefore, what this shows is that x plus z times x plus z is less than zeta. And crucially, x plus z is greater than x. So therefore we've got a number, x plus z, which when multiplied by itself is less than zeta, but which is also greater than the original number x that we chose in our set. So that's part 3 of the definition of a cut. Therefore the set that we're talking about here is indeed a cut. Okay, so continuing with the proof, if we denote the set that we've just constructed by xi, so denote the set just constructed in fact, rather than say set, I should say cut, because it was a cut that we just constructed. So the cut just constructed by xi. Now suppose xi times xi is greater than zeta. So in this case, we can choose z such that xi times xi is greater than z is greater than zeta. So z is a rational cut, and we've already seen theorem, I can't remember the number, between any two cuts we can always find a rational cut, maybe theorem 160, I can't remember. Okay, so this means that z is a lower number for xi times xi. So when I say z is a lower number, I mean z as a rational number in the old sense. Z is a lower number for xi times xi. So z will be equal to x1, x2, where x1 and x2 will themselves be lower numbers for xi. Okay, so remember what is meant by the product of two cuts. Doesn't matter if the two cuts are the same, it's the set of all numbers that can be written in the form which is a lower number of this cut multiplied by a lower number of this cut. So x1 is a lower number of xi, x2 is a lower number of xi. Now actually it doesn't matter if we interpret this as a rational number in the old sense or a rational number in the sense of definition 41, but we can say that x1 is going to be less than xi and x2 is less than xi, which means here I'm definitely talking about x1 and x2 as cuts. So you can kind of jump in and out of the different interpretations of the notation here. So let x be the maximum, maybe not maximum, let's I'm going to say the greater of x1 and x2. So therefore z is going to be less than or equal to x times x. And certainly x is going to be less than xi, because x is either equal to x1 or x2, whichever is the greater. But both x1 and x2 are less than xi, so x must be less than xi. And x is less than xi means that x is in our set that we constructed previously. So therefore, from this we can say that x times x has to be less than zeta. So both of these bits of information together tell us that z is less than or equal to x times x, which is less than less than zeta, which is in contradiction to what we said up here, because z was chosen to be greater than zeta, but this is saying that z must be less than zeta, so there's a contradiction. Therefore xi times xi is not greater than zeta, so xi is not greater than zeta. Let's do the same thing now for the other direction. So suppose xi times xi is less than zeta. So choose z such that xi times xi is less than z is less than zeta. Then that means that z is an upper number for xi times xi. So I think it was theorem, let me just check actually, theorem 159 maybe. Sorry, theorem 160. Theorem 160, yeah, theorem 160 says that if z is effectively an upper number for a product of two cuts, then z can be written as two numbers, the product of two rational numbers, both of which are upper numbers for respectively each of the cuts in the product here. So x1 is an upper number for xi, so therefore x1 must be greater than or equal to xi, and similarly x2 must be greater than or equal to xi. So that was theorem 158, I think. And let x be the smaller of x1 and x2. Then in that case we get that z is greater than or equal to x times x, and also x is going to be greater than or equal to xi. Again, x is either equal to x1 or x2, and because both x1 and x2 are greater than xi, then x must be greater than xi. So this would suggest that x times x is greater than or equal to zeta, since x is not going to be in the set xi, and the set contains this cut, should I say, contains all the x's such that x times x is going to be less than zeta. So in this case, x times x must be greater than or equal to zeta. So therefore we get that z is greater than or equal to x times x is greater than or equal to zeta, which is a contradiction to what we've got here. Z was chosen to be less than zeta. So the final conclusion here then is that xi times xi is not less than zeta. And therefore, if xi times xi is not greater than zeta and it's not less than zeta, then it must be equal to zeta. Which is exactly what we needed to show. And that completes the proof of Theorem 161. So let's just have a very quick look at the very last section really of this part on cuts in Landau's book. So here we've got definition 42. Any cut which is not a rational number is called an irrational number. Be careful at this stage, just because we've said what we mean by an irrational number doesn't actually mean that there are any. And that's where Theorem 162 comes in. There exists an irrational number. So this is really the thing that fills in that gap. Until this point, all we've had is the possibility of there being cuts or numbers that are not rational numbers. But like I've said previously, up until this point we haven't actually verified that. We haven't shown that every cut is every number is a rational number, or that there exists a number that is not a rational number. That's where Theorem 162 comes in. I'm not going to go through the proof of Theorem 162. Actually, it's not that long. It's just I think that the video's gone on for long enough already. But this amounts, the way that this is shown is to effectively solve the equation xi times xi equals 1 primed. So the existence of a solution to this is guaranteed by Theorem 161. It's then simply a case of showing that the cut xi that satisfies this is actually what we would call an irrational number. And just going back to one of the previous theorems, possibly Theorem 157, which says that every rational cut has a least upper number. So I said that this is an important theorem, and it is because it really gives a structural difference between a rational number and an irrational number. So how would you distinguish the two? Well, you look really at the set of upper numbers. For a rational number, if you look at the set of upper numbers, if you've got a least one in there, then it's a rational. It's definitely a rational cut that you've got. On the other hand, if you look at the set of upper numbers and there isn't a least number there, then it's an irrational cut that you've got, an irrational number. So, like I said, I'm not going to go through through this. What I just want to touch on just before I finish this video is maybe how to visualize cuts. Or one visualization that I commonly see is that if you think of kind of the real number line, and you literally cut at a certain point. So this is the increasing direction of increasing in value. So down this end, you've got all of the numbers in your cut, and up here you've got all of the numbers that are the upper numbers, effectively, and the lower numbers down this side. So lower numbers and upper numbers. I personally don't like this visualization of a cut, particularly at this stage, really because this gives the impression that all of those numbers are already there, that all of these irrational numbers and everything, that they've already been constructed and are already there, and we can just cut wherever we want. We can cut at a rational number and we can cut at an irrational number. which how can we really cut at an irrational number if that irrational number hasn't even been proved to exist? We don't even know that it exists. So I don't like this visualization, at least at this stage. I would much rather visualize things as possibly just two circles, as simple as that. So in one circle we've got all of the lower numbers, and here we've got all of the upper numbers. Remember, we only separate the rational numbers into lower number and upper numbers. These irrational numbers at this stage, they don't really come into the picture. We can't call an irrational number either a lower number or an upper number. It doesn't make any sense at this stage. So we just split the rationals. I don't think of them as lying on a real number line or something like that, because the real number line, as far as we're concerned, hasn't been constructed yet. We don't know anything about the structure of it. Maybe further down the line we can think about things like that, but we can't yet. So even in a kind of hypothetical sense, we can't cut the real number line because it hasn't been constructed yet. So we are literally just separating going through the rational numbers, so to speak, and just deciding, yeah, that's in lower number, the set of lower numbers, that's in the set of upper numbers. And then the set of lower numbers we just call our cut. And then this set of upper numbers is just the set of upper numbers. It's the set of numbers that is not in our cut. So this really makes it easier for me personally to visualize, even though obviously it doesn't look quite like anything's been cut in the sense that the real number line here is being cut. It doesn't give quite the wrong misleading impression that this gives, particularly at this early stage where things haven't been fully constructed. So that's the last really thing that I want to say regarding these cuts. So that brings us to the end of this video. The next video is going to be moving on to the real numbers. It might be one, might be two more videos to go, I don't know. But thank you for watching this video, and I'll look forward to seeing you in the next video.